In the previous video, we looked at autoencoders, which compress input data and then reconstruct it. In this video, we'll take it a step further and explore variational autoencoders and conditional variational autoencoders, which allow us to generate data that meets specific conditions. First, let's briefly explain standard autoencoders. An autoencoder is a neural network-based nonlinear method composed of an encoder, a latent space, or latent vector, and a decoder. The process starts when high-dimensional input data passes through the encoder, which compresses it into a lower-dimensional latent space. Then, using the information from this latent space, the decoder reconstructs the data back to its original dimensions. During training, the model learns to minimize the difference between the input and output, effectively capturing the most important features. Because of this, autoencoders can be applied to tasks like anomaly detection, recommendation systems, and noise reduction. We mentioned that autoencoders use a low-dimensional latent vector created by compressing the input data. For example, if we represent the latent space in 2 dimensions, a traditional autoencoder takes an input x and passes it through the encoder, which produces a latent vector z, say z1, z2, corresponding to that input in the latent space. This vector is then fed into the decoder, which reconstructs it back into the original data, with the ultimate goal of producing an output that matches the input as closely as possible. A variational autoencoder, or VAE, is a probabilistic generative model. Unlike a traditional autoencoder, a VAE doesn't produce a single latent vector for each input x. Instead, the encoder defines a normal distribution with a mean and a standard deviation. So, if you have 100 input values, you end up with 100 different normal distributions. The VAE then randomly samples a latent vector z from these distributions and feeds it into the decoder to reconstruct the data. Thanks to this process, a VAE can generate multiple different outputs from a single input and allows the latent space to be explored in a continuous and probabilistic way. As you can see in the figure, the encoder outputs a probability distribution in the latent space based on the input data. Specifically, the encoder calculates the mean and standard deviation from the input to define a normal distribution. Then, to obtain a latent vector z, it uses noise sampled from a standard normal distribution. This latent vector z is then passed to the decoder, which reconstructs the input data. In other words, the latent vector is generated by combining the mean, the standard deviation, and the sampled noise. As we explained in the previous slide, the latent vector is obtained by combining the mean, the standard deviation, and noise. This is done through the reparameterization trick. Mathematically, it's expressed by multiplying the standard deviation with the noise and then adding the mean. Here, the noise is randomly sampled from a standard normal distribution. Thanks to the reparameterization trick, this sampling process is both probabilistic and differentiable, allowing backpropagation. Additionally, because of the noise, even the same input can produce different latent vectors each time, enabling a continuous and probabilistic exploration of the latent space. As we saw in the previous slide, even the same input can produce different latent vectors each time, depending on the sampled noise. In other words, as shown in the figure below, different latent vectors are generated based on the noise, and the decoder uses these to produce outputs that differ from the original input. In other words, it could generate a smiling version that's different from the original image. Thanks to this structure, a variational autoencoder goes beyond being a simple reconstruction model and is classified as a generative AI capable of creating new data. Let's summarize and compare a standard autoencoder with a variational autoencoder. A standard autoencoder compresses input data into a latent vector and then reconstructs it through the decoder. In a standard autoencoder, each input produces a single fixed latent vector, and the latent space is irregular and discontinuous. As a result, the output is limited to a reconstruction that closely resembles the input, and the model has almost no ability to generate new data. In contrast, a variational autoencoder represents the latent vector as a probability distribution, a normal distribution defined by a mean and standard deviation. Each input defines a different distribution, and latent vectors are obtained by sampling from this distribution. This allows multiple different latent vectors even for the same input, and the decoder can generate diverse outputs by sampling from the distribution. Moreover, VAE has a continuous probabilistic structure of the latent space, meaning that exploring or interpolating within the latent space produces meaningful changes in the output. So far, we have looked at variational autoencoders. Now let's take it one step further and explore conditional variational autoencoders, which can generate data that satisfies specific conditions. A conditional variational autoencoder, or CVAE, is an extension of a variational autoencoder that enables conditional data generation. As we discussed earlier, a VAE learns a latent variable z from input data x and generates data based on it. In contrast, a CVAE takes additional conditional information y, such as labels or class information, along with the input data, allowing it to generate data that satisfies the specified condition. Specifically, the encoder receives both the input x and the condition y to estimate the probability distribution of the latent vector, while the decoder combines the sampled latent vector z with the condition y to produce outputs that reflect the condition. Let's take a closer look at conditional variational autoencoders. In a variational autoencoder, each input sample x is passed through the encoder, which defines a normal distribution with a mean and standard deviation. A latent vector z is then randomly sampled from this distribution and fed into the decoder to reconstruct the data. In this way, a standard VAE aims to either reconstruct the input data or generate new data similar to the input. In contrast, a conditional VAE incorporates both the input data x and additional conditional information y. The encoder takes x and y together to estimate the normal distribution of the latent vector z. The sampled z along with the condition y is then passed to the decoder, allowing the CVAE to generate data with desired characteristics that correspond to the specific condition y. Let's compare a standard variational autoencoder, VAE, with a conditional variational autoencoder, CVAE. A standard VAE learns latent vectors z solely from the input data x and reconstructs data based on these vectors. It does not use any conditional information, so the ability to control the generated outputs is limited, and it mainly focuses on general data generation. In contrast, CVAE takes both the input data x and additional condition information y into the encoder to estimate the distribution of the latent vector z. The sampled latent vector z along with the condition Y, is then passed to the decoder to generate data. This allows the CVAE to produce outputs that satisfy specific conditions, making it more suitable for controlled, condition-based data generation. This slide illustrates data generation and application examples using a conditional variational autoencoder. CVAE maps input data and condition information simultaneously into the latent space via the encoder, and the decoder then reconstructs data using the same condition information. This allows selective generation of data with specific attributes or conditions, making it applicable across various fields. In particular, it can be used for tasks such as generating formulations ratios through inverse design for developing foods with desired quality characteristics, designing composition or structure to achieve materials with specific physical properties, or designing drugs with targeted efficacy.